Let's go back to the kinetic molecular theory of gases a little bit, the KMT. And the KMT does a pretty good job with gases, but there are some assumptions, and some of the assumptions are better than others. And we're going to look at some of the places where the assumptions are kind of weak. So one of the ideas in the KMT is that gases are constantly moving around, all right? Unless you get to 0 Kelvin, there's always going to be movement. The gases will be in constant motion. And the motion a lot of times will be pretty random. And that's a pretty good assumption. I've got no problems with that. This one's kind of interesting. The pressure that arises when you measure pressure, it arises from collisions of the gas with whatever kind of walls you're containing. So if you have like the pressure from a barometer column, the pressure is like smashing into the column, making it go bigger. Pressure they feel really is from collisions of gas molecules with a container. And this actually works pretty well. So if you've ever been curious where pressure comes from, it's just from all the little gas molecules kind of smack, 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 smack on the sides of the walls. Kind of interesting. In the KMT, they assume there's no attractive or repulsive forces between the gas molecules. They also assume that the collisions between the gas molecules are elastic, i.e. no energy is destroyed. Now this one we're going to start running into some problems with. We're going to assume in Chem 222 and Chem 223 that all gases have no of these attractive or repulsive forces. In the next chapter, we're going to refer to these attractive repulsive forces as intermolecular forces. And gases generally don't have a lot of these forces going on, but there are some. And this one can lead to some problems sometimes. So just realize that it is an assumption. It works pretty well, but we're going to see that sometimes those IM forces in the next chapter can interfere even with gases. In our classes, we will assume that gases don't have these forces, but in the real world, sometimes they do. The other one, which we've already run into problems with too, is that the volume of the gases is negligible. Like we don't have to worry about the molecules. We worry about the volume the gases take up, like the liters and stuff like that. However, as we saw in the earlier discussion with Charles, as you go to 0 Kelvin, the volume goes to 0, and that's pretty lame. So the last two, there are some issues with when it comes to the assumptions. The first two are pretty good. All right. If you're curious, you can see the principal assumptions of the kinetic molecular theory handout in the companion and on the website, but you can at least start with the first two and know those are pretty good. And the next two, we have to be a little careful of, but we can make them work. We're going to take a little break into physics here for a little bit and talk a little bit more about ways that KMT can be used. But to do that, we really need to talk a little bit more about the equations used to describe the energy of the molecules and also how the energy relates to the temperature of molecules. And again, from physics, if you've taken physics, cool, and if you haven't, don't worry about it. But the energy of movement is usually seen as kinetic energy. And kinetic energy is just a type of energy. And like all the enthalpy stuff we've done so far, energy is measured in joules. So from physics, the energy of movement, the kinetic energy, equals 1/2 mv squared. And m here is just the mass. The mass is usually in kilograms, all right, or kilograms per mole. The v is for the velocity, which is like speed, how fast it's going. And speed is usually measured in meters per second. So 1/2 mv squared is the way to calculate the kinetic energy, like how many joules it's moving. But you can use that kinetic energy to also talk about the relationship of the temperature of the gas as well. And kinetic energy also equals 3/2 times RT. And this R is the energy R I talked about in an earlier slide, 8.3145 joules per mole Kelvin, and the T value is the Kelvin temperature. All right, so this line right here is just a way to see that these are ways that people talk about kinetic energy. But here's where it gets really interesting. At the same temperature, all right, all gases have the same average kinetic energy, all right? As the temperature goes up, the kinetic energy also goes up. Now, you can't change the mass of a gas, all right? Helium is always going to be about 4 grams per mole, and it doesn't matter if it's 2 Kelvin or 200,000 Kelvin, it should always be 4 grams per mole. So if the temperature changes and the 1/2 mv squared equals that 3 FRT, the thing that changes will be the speed, V. As temperature goes up, the speed of the gas goes up. And as temperature goes down, the speed of the gas goes down. And I like this analogy because I feel that way in my day-to-day world. If it's cold outside and I have to like go to Mount Hood Community College to teach, like I'm a little bit more sluggish. I'm like, oh, I'd sure like to stay home today and read a book or something, you know. The temperature makes me not quite as active. On the other hand, if it's a nice day and I'm like, boy, what a beautiful day, I'm more enthused and I get ready and I get to Mount Hood a little faster and stuff like that. So I feel that as temperature changes, my speed goes up and down too. My mass does not change unless I diet, which is a whole different story. Don't get me started. Anyway, we're not going to go there. Temperature affects me. Temperature affects gases too, and it affects it through the speed. So we're going to see here in a little bit how temperature makes the speed go up, and temperature, or if a temperature goes up, and temperature, if it goes down, it makes the speed go down. And these equations right here are actually the way to get numbers out to verify that these things are happening.
Gas molecules are in constant motion and frequently collide with one another. Although not all the molecules in a gas sample move at the same speed, the higher the temperature of the gas, the greater the average speed and kinetic energy of the molecules overall. This higher level of energy allows molecules to disperse more readily, which is one reason we smell aromas better when temperatures are higher.
So this video kind of shows what I was talking about earlier, but this, instead of babbling about me going slow or fast because of the temperature, this is showing the actual gases. So as the left-hand side, you got a hot temperature, and the right-hand side, you have a cold temperature. And you can see at the cold temperature, the gases kind of go a little slower. They bump into each other, and then they go off in their own directions and stuff, but it's a much more mellow environment. On the other hand, in the left, at the hot temperature, man, those gas molecules are active and they're bouncing around, going faster, and they bounce into each other and stuff like that. Well, the left-hand side would be like me on a warm day. I'm a little bit more with it. On the other hand, the right-hand side, the cold temperature, that's me on a cold day. It takes a little bit more energy to do things and stuff like that. At the same temperature, all gases have the same average kinetic energy. All right, that's that 3/2 kT thing. But what happens then is as temperature goes up, the kinetic energy goes up as well, and that means the speed will change. The mass, 1/2 mv squared, the mass part doesn't change, but the speed will. So that's why at the high temperatures, those gases were going crazy. On the low temperature, it was much more mellow. Speed was higher on the left, speed was lower on the right. Maxwell wrote the equations that scientists still use to this day, and this is one of his equations. And you can see it's really weird. It's the square root of u squared with a line over it, and that equals square root 3RT over m. There's a lot of interesting things you can glean from Maxwell's equation, but here's what we want to realize. That u there is the average speed, all right? It's what they call the root mean square speed. And scientists use that. We don't need to worry about that right now. But think of that as the speed component, like how fast something goes. And you can see on the other side, if you get rid of the square roots, you basically square them both and get rid of them. The speed depends then on 3RT over m. Now 3 and r are constants. They're boring, but you can see that speed and temperature are both in the numerator. So that means as speed goes up, the temperature goes up. As speed goes down, the temperature goes down. However, the molar mass is a player. Molar mass is in the bottom. So what that means is small molar masses will have higher speeds. They're opposite because they're on opposite parts of the math. On the other hand, bigger molar masses that are large, will have smaller speeds. So Maxwell's equation is cool because it shows directly this relationship between the speed of a molecule and the temperature of the molecule that it's experiencing. And it also shows how the molar mass of the gas will make a speed of a gas go up and down. So speed increases with increasing temperature. And that's what we also saw in the last slide. 1/2 mv squared equals 3/2 kT. Speed and temperature were on opposite sides. Absolutely, it's going to make a big difference. On the other hand, speed will decrease as you increase the molar mass. And this may not be too intuitive, so let me use an example. Let's say that there's a runner who's Olympic quality, a really good runner, and they decide to run with me on the Mount Hood track, the Mount Hood track there where it's a 1/4 mile or something like that. And I say, yeah, no problem, all right. So I go down there with this Olympic runner, and there's no way. I mean, I'm not in bad shape, but I'm not in very good shape either, all right? And this person, if they can do the Olympics, would be really fast. So if we had a race, this person would just kick my bottom because they are in really good shape. Their mass is probably smaller, so their speed would be higher. And on the other hand, I like pizza and JoJo's way too much, so my mass is probably bigger, and bigger mass is going to have smaller speed. So you can use this idea with running, all right? Heavier people go slower, lighter people go faster. Heavier gases go slower, lighter gases go faster. So all of this is just trying to rationalize the behavior of gases and what you see when you analyze gases.
Cars on highways travel at a variety of speeds. To show the distribution of automobile speeds, we could plot the number of cars moving versus their velocities. Molecules in the gas phase show the same variability of speed. Plots of molecular speed distributions are called Boltzmann plots.
When you drive on the freeway, you certainly don't see everyone going the same speed. I like to think of myself as like a middle-of-the-road driver, all right? Like if the miles per hour limit supposedly is 65, I might go a little bit more than 65, all right? Always looking for police and stuff like that. But anyway, I'm kind of the average driver, and you can agree or disagree with me as you want. However, there's always going to be the people out there, senior citizens, whatever, and, I'm not going over the speed limit, so they go like 50 miles per hour in a 65 mile per hour zone, and it always makes me really happy, but that's another story. Anyway, they're really slow, all right? On the other hand, then there's the people that watch Fast and the Furious movies a lot more than I do, and they're just zipping by me, man. I'm like, whoa, and I'm kind of envious, but I'm also kind of like, those darn drivers. So anyway, this is all silly, but on a freeway, or any road for that matter, you're going to see a whole bunch of different speeds, all right? Some people drive hyper fast, some people drive really, really slow, but there's usually like an average speed, all right? And that probably depends on all kinds of conditions, but there will be an average speed. And in all of these discussions so far, gases are a lot like people driving, all right? Some of the gases are just going crazy. They just got tons of energy and they're just busting out. On the other hand, some of them are senior citizens. They don't have a lot of energy and they're moving very slow, but there will always be an average. And what scientists use when we talk about the KMT and how it applies to gases, we usually think in terms of an average speed. Like, what are most of the gases traveling at? What is their velocity in meters per second? Something like that. There will be gases that are slower. There will be some that are higher. But again, there's going to be some kind of average. And that that little part right there, that represents the most probable velocity of a gas, all right? And that's what we're talking about in these problems. There will totally be gases that are slower and faster, just like there are drivers that are slower and faster. But we're talking here about the average, the most likely, if you will, speed of a gas molecule. This picture is kind of cool. It shows two samples of oxygen. And the oxygen, the blue line, that represents a sample at 25 degrees Celsius. And the reddish brown line shows a sample of oxygen at 1,000 degrees Celsius. And those curves there, the blue and the kind of red-brown curve, that's just the distribution of the different gas molecules. So you can see at the blue gas, the cold gas, the average gas speed is right there. It's 400-ish meters per second. On the other hand, at 1,000 degrees Celsius, you can see that the average speed for the 1,000 degrees Celsius O2 closer to 800 meters per second. So as we increase the temperature, the average speed went up as well. However, even at the lower speed, all right, there are still some gases down here that, again, these guys really like Fast and Furious movies, I guess. But anyway, those gas molecules at room temperature are still going faster than the oxygen molecules, than a lot of the oxygen molecules at 1,000 degrees Celsius. The average has shifted to a faster speed, but you still have exceptions. And also at 1,000 degrees Celsius, you still have some senior citizen gas molecules down here that are going slow. Now you have less going slow than you did, say, at the colder temperature, which would be a bigger part right there. But you can see that the average has shifted, but you still have slow and you still have fast. And this line probably goes quite a ways out here with some small amount. So this is just showing how people think about gases, and there's always a distribution, all right? Statistics comes in really handy with these kind of analyses because you do have a variety of speeds at any given temperature. The average speed decreases with increasing mass. So remember I talked about how me, the heavy runner, would go slower than the Olympic runner, who's probably a lot lighter. This is a silly version. Actually, my example was silly. This is a practical example of how this works out. Now, again, what we have here is a bunch of distributions of speed, okay? And let's look at the averages again. Here's the O2 average. This purplish line is the N2 average. This kind of green line here is the height water average, and this is the helium average. So you can see here how the averages are moving to the right. And if you look at the molar masses, oxygen O2 is about 32 grams per mole, and N2 is about 28 grams per mole. Water is about 18 grams per mole. I don't know why I wrote water there. I guess I felt like it. Anyway, and then helium, about 4 grams per mole. So 32 to 28 to 18 to 4, and the speeds are getting larger. So that's the way that you can see that the average speed is increasing as the molar mass is decreasing. Or if you go the opposite direction from helium to oxygen, as molar mass gets bigger, the average speed gets smaller. But do realize that even heavy in this little graph thing, oxygen here has some pretty good Fast and the Furious molecules. They can probably get at least close to the average speed of light helium. So it's kind of interesting to see how this works out. In this problem, it's assumed they're all at the same temperature, whatever the temperature is, probably 298 Kelvin. So again, on average, molar mass goes up, this average speed goes down, and vice versa. It's kind of cool to see how these things work out. Diborane, B2H6, burns in air according to the equation we looked at earlier. And in this equation, there are 3 gases, all right? The B2H6, the O2, and the water. The B2O3 is a solid. These kind of rules don't apply to solids. You have to be a gas to have all this kind of cool stuff happen. But anyway, it says place them in order of increasing velocity. So increasing means slowest to fastest, all right? And to answer this question, we need to know the molar masses of the gases, because molar mass, as it goes up, then the speed goes down. So if we want increasing, which means slowest to largest, we want heaviest molar mass first, and then the last one will be the lightest one. So water is a number I know right now. It's about 18 grams per mole. And it's the molar mass we can use to figure out the speeds of these things. Oxygen is about 32 grams per mole. So 2 oxygens, 2 times 16 would give us 32. Boron, I believe, is about 11. Yes, 10.811. I'm going to use 11 because it's easier to add. Secrets of Chemist 101. Anyway, so boron, assuming it's 11, 11 times 2, 22, plus 6, about 28 grams per mole. And again, you can do better with better sig figs, but we just need to see the differences here in the molar masses to appreciate the speeds. So you can see here that the water is the lightest molar mass, the oxygen is the heaviest molar mass, and since we want slowest to fastest gases, we want highest molar mass to lowest molar mass. So I would predict here that the order would be O2, that would be slowest because it's heaviest, followed by the diborane, B2H6, because the molar mass is in between, followed by water. And lo and behold, that's exactly what we get. So you can see what we did. We went from heaviest gas to lightest gas. Heaviest is slowest, lightest gas is fastest. I didn't use super precise sig figs, and that's okay because that was enough of a difference then to show the order of the different gases. So again, notice this relationship between molar mass and speed. We'll see that several times in the upcoming discussions.